Welcome back. In today's lecture, I am going to talk about positive definite matrices. And it is possible to show that using help of this class of matrices, I can able to construct positive definite functions. And we have already seen during the Lyapunov analysis that if I have some kind of system, you can take any system. Suppose that if I will take x dot equal to fx and x belongs to R, and I am assuming, and suppose x equal to 0 is my equilibrium point, and in order to talk about the stability of this equilibrium point x equal to 0, what we have to do, we have to construct some kind of function vx, and which contain all information of a state variable x that is greater than 0 for all x not equal to 0. So this kind of construction is required, vx greater than 0. And after that, we are also going to maintain vx equal to 0 and v dot x should be less than 0 if we are going to talk about the asymptotic stability. If that is less than equal to 0, then I can talk about the stability. Okay. So, and if that is less than equal to 0, then we are telling this condition or this function vx as a Lyapunov function. So we have already seen this kind of definition. Now construction of this function vx is not obvious. Okay, but we have certain kind of guidelines if we have linear system. So linear system means if you have system like axt, or even if the time varying system at into xt, it is possible to show that always I can give guarantee that what kind of Lyapunov function I can construct. Okay, so at least for linear case, we are very much confident that how to construct the Lyapunov function. Okay, most of time people are become confused that why I will construct Lyapunov function for linear case, because that is obvious. I can go via frequency domain and other techniques, and after that I will do the stability analysis. Why Lyapunov analysis? But it is possible to show that several systems, even if they are showing linear behavior, but that is not the actual behavior of the system. Always some perturbation exists. Okay, so if some perturbation like something like dxt comes into picture, then it is possible to show that again construction of Lyapunov function for this system without any perturbation, I can able to talk the stability of the perturbed system. That is another beauty. Okay, so due to that reason, we are very much concentrate on the construction of Lyapunov function, at least for the linear case, linear time varying case or linear time invariant case. And I have already told you that I can give guarantee that what kind of Lyapunov function at least exists for the linear case, but for nonlinear case I cannot give guarantee. And how basically one can give the guarantee? Using the help of this positive definite matrices. Okay, if we are talking about the stability of some nonlinear system about equilibrium point by linearization, then also this method, because finally we are getting some equivalent linear system, so this method works. Okay, and due to that reason, in today's lecture I am not going to talk how to construct Lyapunov function, but I am going to talk that how to select some kind of function like vx greater than 0 with help of positive definite matrices. Okay, and once we understood this, then we are also able to understand what is shape of that particular positive definite matrices, positive definite function associated with positive definite matrices. Okay, and I hope that you are already well aware about the eigenvalue and eigenvector. I have already told you that if you don't know, then please go through any standard textbook. So you can see that I have two different kind of matrices. I am going to talk about a square matrix. What is meaning of a square matrix? That A has, I am going to assume that is n cross n matrix. Okay, so if A is a square matrix and M is symmetric, we all know this definition, M equal to M transpose. Okay, in this whole discussion I am going to assume that each entry of matrix is coming from real number only. I am not going to means consider the complex number. Okay, after that a square matrix M is skew symmetric, that is M equal to minus M transpose. During the matrix course, during our 10+2, we have already learned about this. Okay, and one of the most important feature here that is involved, that if I have any square matrix, it is possible to show that that matrix M can be written as a symmetric plus skew symmetric matrices. Okay, this is obvious, this relation is obvious. I hope that, because M transpose, this represent transpose by 2. I know that, I hope that you are able to understand how to calculate the transpose. And after that you can see here M 2M by 2, so component wise addition is here, so I have M. Okay, and if you check this matrix, so that is always symmetric. We have already defined M equal to M transpose, and skew symmetric M equal to minus M transpose. Okay, after that, based on the matrix, I can able to construct some kind of quadratic function. Okay, so suppose that I have some kind of matrix like n cross n matrix, and here this represents that each entry of matrix is some kind of real number, and suppose this is a skew symmetric matrix. Okay, a skew symmetric matrix, we have just seen the definition, M equal to minus M transpose. And now what you can do, you can select any arbitrary vector. Okay, and here if matrix M is n cross n matrix, then you have to select X, that each entry is real number and that is n cross 1. Okay, and if you do this kind of product, here M is a skew symmetric matrix and X transpose X, you can see that X is n cross one column vector, so it is converted into 1 cross n, and this is n cross n M, and this is again n cross 1. Due to that reason, by matrix multiplication, this is nothing but some kind of a scalar, and if this is a scalar, then now I can able to talk that this is equal to 0, greater than 0, or less than 0. Because if that is not a scalar, I just able to talk about the equality. I do not able to talk about the inequality in general sense. In component wise one can talk, but in general sense I cannot. Okay, and it is possible to show now that if you take transpose on the both hand side, means this side as well as this side, then what happens, that this is a scalar quantity. So suppose that if you have a scalar quantity A and B, so and if you have A equal to B, so even if you can take transpose, so both are equal. Okay, so what happens, suppose since this is a scalar, so either I can A equal to B is some kind of a scalar quantity, so B equal to B transpose I can also write, that is not a problem. Anyone has confusion? That a scalar quantity, and if I will take transpose of that quantity, then both are equal. Anyone? And if you have confusion, then take some kind of matrix which has just one entry and try to calculate the transpose of that. So it is possible to show that remains the same. So due to that reason, you can see that I have this kind of quantity. Now I am going to take the transpose. I am telling that okay, this is A and this is equal to B, so A, B and equal to B transpose. So that kind of things I am assuming here. Now here I hope that you are well aware about this fact that AB transpose equal to B transpose A transpose. Anyone has confusion on this? That if I will take transpose of some quantity multiplication, then that will satisfy this kind of property. So same property I am going to utilize here. What I am going to do, that I am going to consider here this X transpose M transpose as a one bunch of quantity and X as a independent quantity, and if you will do AB transpose, then that is B transpose A transpose. So X transpose, negative sign is here, that persist here, and M into X. Okay, so please just check it. And after that, what happens? What we found, that if some quantity is exactly equal to negative of that quantity, and if both are equal, then I have only one choice. And what is that choice? That is a scalar. So I have choice that this equal to 0. Okay, so what kind of claim now I am going to do? That quadratic function associated with a skew symmetric matrix is always 0. Okay, but if you take the symmetric matrix, then negative sign is not here, and due to that reason we are telling that quadratic function means you can select the appropriate vector, column vector, and multiply with that matrix on both sides and try to convert that into some kind of a scalar function. Okay, so quadratic word is basically come into picture because most of time people are starting with this very simple matrix. Suppose that I have A, B and B and C, something like that. I have considered intentionally, I have considered some kind of a square matrix and symmetric matrix. And here you can see that if I multiply this matrix by x1, x2 transpose and x1, x2 like this. Okay, so after multiplication, if you do multiplication and if you put some kind of number here, suppose 1, 2, 3, 4, something like that, then it is possible to show that after multiplication of this, you are going to get some kind of number, that is some quantity is here, x1 square comes into picture. After that, some delta 1, delta 2, x1, x2 will come into picture, and delta 3, x2 square comes into picture. Like this kind of a structure basically comes into picture, and due to that reason this form is also called quadratic form. Okay, and I am going to talk about generalization. Generalization means now what you can do, you can take any order of this matrix n cross n square matrix, and after that you can it is possible to show that similar kind of form I am going to get. Anyone has confusion till now? So what we found, that some kind of matrix where that will satisfy the property of a skew symmetric matrix, and if I don't have a skew symmetric matrix, some general class of matrix, I have already shown that I can decompose that matrix as a symmetric matrix as well as a skew symmetric matrix. So what happens, quadratic form associated with a skew symmetric matrix is 0, and due to that reason I am going to limit my discussion only on symmetric matrix. Okay, so now I confine my discussion to symmetric matrix because I know that, because what we need some kind of a scalar function which has some kind of property that is positive definiteness. Okay, so for that I have to construct some kind of quadratic function with help of some kind of matrices. Okay, and why basically we are constructing, because it is possible to show in next lecture using this kind of construction I can construct Lyapunov function, generalized Lyapunov function for all classes of linear, time invariant and time varying system. That is our aim. Now if you see the symmetric matrix, so all n eigenvalue lambda of a symmetric matrix S are real number. It is possible to show. Okay, you can take any symmetric matrix and keep each entry as a real number, then it is possible to show that whatever eigenvalue, if I have some kind of matrix n cross n matrix, so obviously I have n eigenvalue. I am not going to talk about what is nature of eigenvalue, means repeated or non-repeated, but it is possible to show that are real number. Okay, I am not going to prove it. An eigenvector q can be chosen orthogonal. Okay, so it means that if I have n number of eigenvalue associated with some matrix A, suppose that if you have n cross n matrix, so in this particular matrix it is possible to show, if you solve this, lambda I minus a determinant equal to 0. That will give us the eigenvalue, n number of eigenvalue. And after that, if this matrix A is symmetric, then and each entry of A is coming from real number, then I know that all eigenvalue lambda 1, lambda 2 up to lambda n, all eigenvalue are real. Okay, and it is possible to show that with, suppose I have some kind of matrix A, so this matrix A, and suppose you have this x is some kind of vector, it is possible to show that is lambda into x. Okay, so here one can interpret this particular vector x as a eigenvector. Okay, and what basically we are telling, that if you select one eigenvalue lambda 1, so with this selection of eigenvalue lambda 1, there is associate one eigenvector x, such that if you apply that eigenvector x like this, then what happens, that this vector remains the same, that is just scale out by some kind of value that is called lambda 1. Okay, that is basically beauty of the eigenvalue. Okay, whenever we are going to talk about the eigenvalue and eigenvector, so what is interpretation? Interpretation is that eigenvector is such kind of operator, if that operate on some matrix, then same vector comes into picture, and that is just scale out by some kind of a scalar quantity that is called eigenvalue. That is the interpretation. Okay, anyone has confusion on this interpretation? Anyone? Baby Diana, are you here?
Yes, sir.
So have you able to understand the interpretation of eigenvalue and eigenvector? I already assume that you are knowing how to calculate, but do you know what is interpretation?
Yes, sir.
Okay, so by showing this simple equation, one can able to see the physical interpretation. Okay, interpretation is that, suppose if you have some matrix A, what you can do, you can operate using one vector, and if that vector is eigenvector, then it is possible to show that vector remains the same. Okay, but that is just a scale by some amount, a scalar amount lambda 1, and that is eigenvalue. So this quantity lambda 1 is called the eigenvalue, and corresponding vector is called eigenvector. So this is very special vector. Okay, and if I have symmetric matrix, then it is possible to show that associated with every eigenvalue I have one eigenvector. So I can choose an eigenvector that is orthogonal, means perpendicular to each other. That is the beauty. And it is possible to show that I have taken very simple case. Extreme example means very simple example. Suppose if I will take some kind of identity vector. Okay, so or identity matrix. This is again R n cross n matrix, where each entry is identity like this, 0 1 0 0, something like this. Okay, so eigenvalue is obviously 1, and that is repeated eigenvalue, and it is possible to show that I have some kind of vector for all x not equal to 0. I have this kind of relationship, because how to calculate eigenvector? Whenever I have some kind of matrix, I have to operate with some kind of vector that is called eigenvector. If that is our eigenvector, then eigenvalue comes into picture and that vector remains the same. So using that formula, I have constructed this. And remark is, what kind of remark we found? That I have repeated eigenvalue like lambda 1, lambda 2 up to 1. If I will take the some kind of matrix where that matrix is identity matrix, and we can choose eigenvector that is again orthogonal, and it is possible to show that I can rescale that vector of unit length. Okay, I will show you using some kind of example also, and it is possible to show that eigenvector q1, q2 up to qn are not only orthogonal, means perpendicular to each other, but they are also orthonormal. And next point 5 is telling the definition of orthonormal, that if I have some kind of eigenvector of matrix S has this kind of property, q transpose q equal to identity, then that is called orthonormal column vector. Okay, so just I am telling some kind of definition, and using help of this kind of definition, what I am going to do now, I am going to talk about the some kind of positive definite matrix. And we now very well aware that just I am going to consider the symmetric matrix. Okay, because main idea, whenever we are telling something as a positive and negative or equal to 0, so equality is okay, I can talk in terms of the vector also, but most of time whenever we are talking about greater than, less than, at that time I have to map some quantity from Rn to R. That kind of requirement we have. So now I hope that you are able to understand the definition of orthogonal or orthonormal. Okay, whenever I have orthonormal, then q transpose q equal to identity, and if you see component wise, then this kind of situation I have. Q transpose q equal to identity means when I not equal to j, at that time I have 0. When I equal to j, at that time that is unity. So if I have some kind of eigenvector, then we are trying to actually scale it out such that their length become unity. Okay, and now we will see this point in the latter part of today's lecture. We can write q instead of x for eigenvector matrix x S, because now we can know that if I have symmetric matrix, so at that time I can rescale orthogonal to orthonormal, okay, by some kind of proper way. And due to that reason, finally if you start with this matrix, where this matrix is nothing but eigenvector, and here eigenvector inverse, and this lambda, entry of lambda is nothing but, suppose that if you know first eigen value is 1, and suppose you have 3 cross 3 matrix, and I have constructed this kind of 3 cross 3 matrix. So here meaning of lambda for 3 cross 3 matrix, I am going to keep all the eigenvalue diagonal, and after that corresponding to 1 I have choose some kind of eigenvector, corresponding to 2 I have choose eigenvector, corresponding to 3 I will choose eigenvector, and I am going to put all eigenvector like some kind of matrix, and after that I am going to generate that matrix. So any matrix can be factorized in terms of eigenvalue and eigenvector. Here I am just going to concentrate on symmetric matrix, not other, a square, and obviously I have a square matrix. Okay, so what happens that I can rescale this eigenvector to unity. At that time I have this kind of representation, because we know that that is not only orthogonal but that is also orthonormal. Okay, till now anyone has confusion, then please let me know. Anyone? Okay, so if you don't have confusion, then let us come to the next theorem. Without proof I am going to tell you this theorem. So every real symmetric matrix, real means whenever I am going to consider the matrix where I am assuming that each entry is some kind of coming from real number, okay, has form this kind of form where q is a matrix of eigenvector satisfying this kind of condition. I have told you that suppose first step I have to calculate the eigenvalue, and corresponding to eigenvalue I have some kind of eigenvector. Okay, and suppose if I have eigenvector, I can scale that eigenvector with the unity vector. Whenever, suppose that if you have x during school time, you might have learned about this. If you have this kind of vector, so I can scale it by unity vector x1 square x square plus y square I plus y by square root x square plus y square j. So similar way I can able to scale it out by unity vector. Okay, some kind of vector where not unity, like this unit length of unit length. Okay, so So and after that what happens, it is possible to show that that will satisfy this kind of condition, and where this inverted lambda is a diagonal matrix containing the eigenvalue. Okay, so in this way I can able to represent any symmetric matrix. Okay, now let us come to the positive definite matrix. Okay, so positive definite matrix, so I have already told you that what we have to do, somehow I have to connect positive definite matrix with the energy. Okay, because whenever we are talking about the Lyapunov function, at that time I am going to talk about the energy like function. Okay, so let us try to see that what is connection between positive definite matrices and energy function. Okay, in another way I am going to tell that if I have positive definite matrix, equivalently I can perform energy test. I am going to tell you that what is meaning of energy test, and I can tell that that matrix is positive definite or not. Okay, so first test is that S equal to S transpose, that real symmetric matrix. Okay, and what basically we are going to tell that a positive definite matrix has all positive eigenvalue. So suppose if you have very small matrix, so you can calculate the eigenvalue. Construct one more important point here, that calculation of eigenvalue for complex matrix is not so easy. You have to do lot of calculation. Okay, if you don't have any software program. So first test is very obvious, that whenever we have a positive definite matrix, then I am going to tell that all eigenvalue that is greater than 0. Okay, and easily you are able to guess that why we are going to tell this, because suppose if I have some kind of matrix A, and what I am going to do that x, then we know that this is lambda into x. Okay, and after that if I multiply both side by x transpose, so here you can see that x transpose multiplication comes into picture, and lambda is just a scalar, so lambda x transpose x kind of quantity comes into picture. Okay, and what we are telling that this matrix A is positive definite matrix. So from, if this is positive definite matrix, then it is possible to show that x transpose Ax is greater than 0. If this is greater than 0, then I have no option. You can see here, because x transpose x is already positive, so only choice I have, that lambda should be greater than 0. And what is lambda? That is eigenvalue of the matrix A, and due to that reason this test comes into picture. Test is suggesting that if you have matrix A, then all eigenvalue of that matrix should be greater than 0. Okay, so if that is not the case, then this relation doesn't remain consistent, because fundamental relation is that if you have matrix A and if you apply eigenvector x, then you are going to give guarantee that eigenvector remains the same, that is just scaled by some scalar quantity, that is called eigenvalue. So that is fundamental relation. And after that, after multiplication of this, I am telling that x transpose Ax is greater than 0. So I don't have any option. Only option is lambda should be greater than 0. So energy based test is actually, so whatever first result that is coming from energy based test, or actually here this test is telling that S is positive definite matrix if energy x transpose Sx is positive for all vector x not equal to 0. Okay, if x equal to 0, then obviously that is 0, that is not positive. So property is almost same like the energy function. You can see that what I am telling, that this should be greater than 0 for all x not equal to 0, and if x equal to 0, then I have 0. Okay, so positive definite S is positive definite if energy of this should be greater than 0. Let us now try to interpret this. So what I am going to do, I am going to take the identity matrix S equal to identity matrix, and I know that eigenvalue of identity matrix is 1. Okay, so if you construct some kind of energy like function x transpose ax, A is identity matrix, you can see that you have condition like x transpose x, that is always greater than 0 for all x. Okay, and due to that reason I can tell that this identity matrix, that is obviously a symmetric matrix, that is positive definite matrix, because that will satisfy this kind of condition, and in another way all eigenvalue is already greater than 0. That is equal, that doesn't matter for me. Similarly, suppose now apart from the identity matrix, suppose I have some kind of matrix x like 2 4 4 9 like this. Again, what you have to do, you have to construct the energy. And how to construct energy? You can take any two vector. It might possible, best choice is the eigenvector. Okay, but now we are going to generalize. You can take any vector, that doesn't matter for me. Okay, and after that if you do this kind of multiplication, after rearranging this is positive, so due to that reason we are telling that this is positive definite matrix. So now if I have to prove positive definiteness of some matrix, there is no need to calculate the eigenvalue or eigenvector. What you can do, test is suggesting that you can select any column vector S, and after that you can multiply for both sides, and if that is always positive, because I have to make sure energy test is telling that for all x this should be greater than 0 when x not equal to 0. So due to that reason there is no need to calculate eigenvalue and eigenvector. So now even if I have 1000 cross 1000 order matrix, if I will perform this kind of test, they will quickly tell us that that is positive definite or not. Anyone has confusion, then please let me know. Now let us come to the, here I have written energy versus eigenvalue. So if whenever I have eigenvalue, then this kind of relation is always satisfied, where what I am telling that S is any matrix, symmetric matrix, and X is the eigenvector, then that is scaled by lambda. Now what I have done, I have just multiplied it, and after that, so lambda greater than 0 leads to this. So these two things are equivalent. Whenever I am telling that some matrix has all eigenvalue are positive, so obviously whatever energy function associated energy function, I am constructing some kind of a scalar function by multiplying column vector both side. So after that what I am telling that is greater than 0, because this relation should satisfy. So if lambda greater than 0, then obviously this is greater than 0, and if this is greater than 0, energy is greater than 0, then lambda should be greater than 0. So both sides, if and only if condition is there. Okay, so this is one of the tests. Whenever you have some kind of positive definite matrix, so that should be symmetric, because if you are go via the energy principle, so in order to construct some kind of positive definite matrix, what you have to do, you have to select some kind of symmetric matrix, and after that you have to just check that all eigenvalue should be greater than 0. If you do not go via that test, then what you can do, you can take any column vector, and after that you can perform this kind of test. Then automatically, if that is greater than 0, then I can tell that S is positive definite matrix. Okay, and for our purpose this is required. So now how to tell that that is greater than 0? Because I have to construct Vx greater than 0. So now what I will do, I know that I have some state x. After that I will take some kind of matrix P here and x. Now question is that when this matrix is greater than 0, so for this P should be positive symmetric definite. PSD I am writing positive symmetric and definite. And from here you are already aware that why I haven't taken some kind of a skew symmetric matrix, because if a skew symmetric matrix, then that is equal to 0. So even if I will take some kind of general matrix that is not symmetric, that is some kind of matrix, general matrix, again I can decompose that into symmetric and asymmetric, and asymmetric part is not going to contribute anything in form of this formation of this energy function. And due to that reason, best thing, just you can select the positive symmetric matrix. Okay, up to here anyone has confusion, then please let me know. Silpi, are you here?
Yes, sir. No, sir.
Okay, so any confusion?
No, sir.
Baby Dina,
Yes, sir.
any confusion?
No, sir.
Because everywhere now I am going to use this matrix, and due to that reason I am asking. This is very very fundamental matrix. Okay, now also we have some kind of equivalent test. Equivalent test is suggesting, suppose I have some kind of symmetric matrix S, then I can represent that matrix like this, A transpose A. Okay, and why we can do that? It is very easy to show. I will show after some time that why any symmetric matrix can be written like this, and where I am assuming that that is independent column. So we are going to show that if why I have taken independent column, why not dependent column is also okay. Okay, independent column means that suppose I have three column A, B, C, so C is not combination of A and B, that is the meaning. Okay, and another test that is suggesting that all leading determinant, okay, we will define what is meaning of leading determinant, that should be positive. Okay, so this test is also important. Most of time we are applying this kind of test, and after that another test is done in terms of pivot of S are positive. Okay, so we will see what is how to define pivot of some matrix, and S I have taken now symmetric matrix without loss of generality. So let us try to see that why I am claiming this, that if S is some kind of positive symmetric matrix, then I can able to represent A transpose A, where A is some kind of matrix. Okay, now here let us try to see that I can also tell that here in this particular problem, since I have to generate S as a some kind of S that is a square matrix. Okay, so properly I have to select some kind of A, and here suppose I have 2 cross 2 matrix I want to create. So now what is beauty? Even if I will take 3 cross 2 matrix, then transpose of that is 2 cross 3, and after that 3 cross 2. So even if A is non-square matrix, that works. Anyone has confusion on this? Then please let me know. So first property is that if S is symmetric matrix or positive definite matrix, then I can able to represent like this, and where A is the whatever column if you see, that is independent column, and after that leading determinant should be greater than 0, and after that third test is called pivot test. Okay, so let us try to see that why I am able to do this. S equal to A transpose A. So if you calculate energy associated with this matrix, then that is X transpose S into X. Okay, and now I am telling that I can able to represent this by A transpose A, and what I am going to do, I am going to group it, and we have already seen that AB transpose is nothing but B transpose A transpose. So, and due to that reason X transpose A transpose is nothing but AX transpose of this and AX, and after that you can see that that is nothing but the length of this, because same quantity is there. So X transpose X, if suppose here Y you can define, so Y transpose Y is nothing but norm of Y square. Okay, so similar kind of quantity here comes into picture. It means that that is going to represent the length of A and X if you do this kind of multiplication, and A is some kind of, suppose this is 2 cross 2 matrix, so X I have to select 2 cross 1 matrix, and if you multiply this, then 2 cross 1 matrix comes into picture, so that will represent the length of some kind of vector. Okay, so a square of the length of some vector, that is always positive, and due to that reason I am telling that S can be represented by matrix A transpose A. Okay, and why independence is required, you try to see that from one example I am going to check. From here I cannot able to comment, because here if you represent this, then always that is positive, AX greater than equal to 0. Only one possibility I have, that might be 0 also. So greater, because this is nothing but length, so length should be greater than equal to 0. Okay, so greater than equal to 0, so equality condition we have to check that when equality condition comes into picture. So for that what we have done, here you can see that I have already told you that a matrix, even if this is 2 cross 2 matrix I have, but I can able to now construct some kind of matrix that is might be 2 cross 3 and this is 3 cross 2. So then finally I can recover 2 cross 2. So a square matrix can be written in form of multiplication of two non-square matrix. Okay, now if column is dependent, here you can see that why I am telling that this is depending on these two. Let us try to check that it is possible to create this kind of matrix based on the combination of these two or not. Okay, if we are able to do that, then I can tell that this column is dependent. Okay, if not, then that column is not dependent. Okay, so it is possible to show that job you have to do, that if you take 1 and 3, then that can be represented in the combination of 1 1 and 1 2. That is obvious. Okay, so I am assuming that this is dependent column. So if that is dependent column, then it is possible to show that multiplication is like this. Okay, and if you multiply with this kind of vector, it is possible to show that is x transpose x 1 minus 2, energy becomes 0. So for non-zero vector I have energy equal to 0. Okay, and due to that reason people are suggesting that do not contain some kind of vector which has dependent column. Okay, so what third test is suggesting that whenever you have some kind of matrix, then try to decompose that matrix like A transpose A. If you are able to do that, then at least you have positive semi-definite matrix. Semi-definite matrix means lambda is not negative but might be 0 somewhere. Okay, if A is column of A is independent, then what happens, that whatever energy function you are going to construct, okay, that is greater than equal to 0 for non-zero value of x. Okay, so same kind of things I have written. A transpose A is at least semi-definite because this can be represented like this, length of some vector square is never negative. Okay, so if that is never negative, it might possible that is 0. Okay, so that is called semi-definite, and you might have seen that whenever I am talking about positive definite function, at that time I was also talking about positive semi-definite function, because Vx should be greater than 0, Vx equal to 0, that should be 0, and V dot x should be less than equal to 0. So that is nothing but positive negative semi-definiteness we are telling. So that requirement is also during our analysis. Okay, so how to check semi-definiteness? So some eigenvalue that equal to 0 is also allowed in that particular situation. Okay, anyone has confusion? So a story is very, very simple, that if you have some kind of matrix, then all eigenvalue associated with that matrix, if that is positive, then energy function associated with that is positive definite. Okay, so now in order to construct energy function, just you have to see the matrix. Okay, and you have to make sure that all eigenvalues should be greater than 0. Okay, another test most of time we are doing, because I have already told you that sometime I have 1000 cross 1000 matrix, and if I have 1000 cross 1000 matrix, then calculating eigenvalue is not a simple task. So another task we can perform, if you have any a square matrix, what you can do, you can just see the leading diagonal. Okay, so like this you can construct this first, so this should be greater than 0. If after that you can come little bit below, and after that you have this kind of matrix now. So check that their determinant d1 is determinant, so determinant of this is 2. After that you can calculate determinant of this, so 2 cross 2 4, and after that minus 1, that is 3, and after that calculate the determinant of whole matrix. If that is greater than 0, all are greater than 0, it is possible to show that S is positive definite matrix. Okay, and you are able to check this by simple analogy like this. What basically we are doing, suppose that if I have A, B, B, C, this is symmetric matrix, and whenever I am going to calculate the energy of this. So energy function or positive definiteness of this, what I am going to do, I am going to multiply with this vector x1, x1, x2. Okay, if you do multiplication of this, then you have some situation like ax square, and after that something comes into picture plus bx2 square. Okay, next part of this lecture I will show you that if lambda 1 and lambda 2 is the eigenvalue, then product of both eigenvalues should be greater than 0, and lambda 1 plus lambda 2, that is, should be greater than 0. Okay, so you have some kind of quadratic function now, and you know that you have root of the quadratic function, that is lambda 1 and lambda 2. Okay, so what you can do, if you have some kind of matrix, then using this kind of equation lambda I minus a equal to 0, you can form some kind of quadratic function and check lambda 1 dot lambda 2, that is greater than 0, and lambda 1 plus lambda 2 greater than 0. Okay, it is possible to show that same kind of condition will appear. Okay, so for us proof is not so important. So what we have to do, we have to just whenever I have some kind of matrix, then what we are going to do, we are going to just see the leading diagonal, matrix associated with leading diagonal, and after that we have to just check that all are positive or not. Okay, and whenever we are defining the pivot, so pivot basically we are defining like this, dk by dk minus 1. Okay, so dk by dk minus 1, what does it mean? Suppose if you are at first place, and we will do one example also, then things become little more clear to you. D1 is 2, D2 is 3 by 2. There, whenever we are going to talk about pivot, here D1, before that there is nothing, so that remains 2. Here that is 4 by 3, so that is called pivot. And using help of pivot, I can able to do lot of things. Due to that reason I am defining this. Now let us try to see, suppose I have some kind of matrix, then I can able to do the factorization of that matrix, and S is some kind of symmetric matrix, and it is possible to show that symmetric matrix can be represented like this, that is L has a 1 on the diagonal entry, and U contain the pivot. Okay, just we know how to calculate the pivot. I have to calculate the leading determinant, and after that what we have to do, we have to divide dk by dk minus 1. Okay, so what if I know the pivot, then I can able to represent matrix like this. I have 2 minus 1 0 minus 1 2 minus 1 0 minus 1 and 2. So check here, S is S transpose. If you S is some kind of symmetric matrix, please check it, and after that you can see here that every entry here, that is 1, and this is nothing but the pivot. Okay, so by elimination one can able to write this matrix with the multiplication of two matrix, and so symmetric matrix can be represented by L, lower diagonal matrix, and upper diagonal matrix. And what is diagonal of upper diagonal matrix? That is pivot. And what is lower diagonal matrix? That is nothing but unity. Okay, now if I pull out all the pivot, I can able to represent matrix like this. Okay, so now you can see here that here as a this is nothing but some kind of pivot, and here 2 3 4 all 2 3 by 2 and 4 by 3, that is pivot. So I have represented this matrix by D and this matrix by L, so I can able to write S equal to LD L transpose. Okay, so in that way also I can able to represent that matrix. So in this way, if I have knowledge of the pivot, now these two things you can see, I have X transpose X, so this D, so if that is greater than 0, so I can tell that there is positive definite matrix. Anyone has confusion? So this is just like energy test. Okay, now this quantity and this quantity X transpose, and after that this, so if these all are positive, so I can able to tell that S is positive definite matrix. So just we are checking the sign of this. Okay, now I have already told you that if I have some kind of matrix, they symmetric matrix, then and if that is positive definite, then I can also able to write A transpose A. So from this example it is possible to show that one can write like this. Okay, so main theme, what we are going to use here, that whenever I have matrix, then what I am going to do, that I am going to calculate d1, d2, d3, and after that I am going to check that all should be positive or not. Sorry for that. Now let us try to check the positive definite matrix and minimum problem. Okay, how basically positive definite matrix is related to the energy function, because what Lyapunov theory is telling, that if some function Vx is greater than 0, and if x equal to 0 and V dot less than 0, then finally I can land up to the equilibrium point asymptotically, x tending towards 0 as t tending towards infinity. So this kind of condition, and x trajectory ball of xt also remains bounded. That kind of condition we have. Okay, so it means that if I have positive definite matrix, so somehow and if this kind of condition is satisfied, then I can able to land up to the minima. Okay, so let us try to check how basically positive definite matrix and minimum problem is related. Okay, so I have selected very simple 2 cross 2 matrix, and now 2 cross 2 symmetric matrix is positive definite. I have already talked about several tests. So first test is all eigenvalues should be greater than 0. So I have written lambda 1 greater than 0 and lambda 2 greater than 0, and how to calculate lambda. So lambda minus s, determinant equal to 0. So in that way you can calculate value of lambda 1 and lambda 2, just check that is greater than 0. Okay, another way, I have already told you that dk, you can calculate d1, d2, dk. So here, that is this a, that should be greater than 0, and after that ac minus b square greater than 0. Okay, and I have told you the proof. You can calculate the determinant, and after that this determinant had 2 root, because I have 2 cross 2 matrix. So just check if 2 root, that is since for positive definiteness this matrix should be greater than 0, so summation also greater than 0, and product that should be also greater than 0. So if you will do these two check, then finally this condition appear, a greater than 0 and ac minus b square greater than 0. So do by yourself. Okay, and I know that how to calculate pivot. If I know d1 and d2, then d1 remains the same, and d2 is dk by dk minus 1, due to that reason this. Okay, another thing, that if I have positive definite matrix, then I can construct energy also, and energy function I can construct like this. I will take some vector x and y, and after that I have matrix, and after that I am going to multiply with that should be greater than 0. So due to that reason this comes into picture. Okay, so I have taken very simple matrix, and after that, in order to develop some next intuition of minima, what I am going to do, that I am going to take S equal to, that this is symmetric matrix, please check it. Symmetric matrix means S equal to S transpose, and after that you can see that this particular quantity is greater than 0. Okay, how to prove this is greater than 0? Just you have to do some kind of adjustment. So here 8 is here, so you have to adjust this quantity such that some quantity from here, that is merge here, and finally what you have to show, or I will show you, then things become more clear. So 2ab, so you can see that if I will write 2x into 2y, and in this side if I will collect that something 2 into 2ab, so if I will collect something like 4x square from here, and here 4y square, you can see that I have one quantity x square plus y square, and after that I have 2x plus 2y, that square, then everything can be written in form of a square. Due to that reason, that is greater than 0. Anyone has confusion on this? Anyone? Why that is greater than 0? Okay, if you don't have confusion, now what you can do, if you draw this, okay, so if you draw 5x square, 8xy, 5xy, so I have some kind of function v you can define. So I have drawn this. So I have two plane x and y, and after that this is energy function. It is possible to show, you can see that I have curve like this, and in this ball minima is here, located here. Okay, so ball is actually upward. Okay, so if energy is always greater than 0 and 0 at 0 and E dot less than 0. So finally you come up to the minima. Okay, and what basically calculus is suggesting, during calculus you might have seen that for ordinary function fx has, if they have only one parameter x, then how basically we are calculating minima? First we are checking that df by dx equal to 0, and after that we are checking the second derivative. If that is greater than 0, then we are telling that x equal to x0. Suppose that if we are checking at x equal to x0, without loss of generality I can shift x equal to 0 to the 0. Okay, so in that way I can check the minimum of some function. But most of time what happens, that problem is not so simple. It might possible I have more than one dimensional function. So suppose that fx is function of x and y. Just we have seen that if I have second order system or 2 cross 2 matrix, at that time what happens, that energy function has two variable x and y. So how to solve minimum problem? At that time again dou f by dou x should be 0. So I have some kind of, if you calculate dou f by dou x, then actually what happens, some kind of matrices comes into picture. Okay, dou f by dou x means dou f by dou x1, dou f1 by dou x2 and dou f2 by dou x. So dou f1 by dou x1, this kind of situation comes into picture, dou f1 by dou x2 and similar kind of things that comes into picture. If I have two variable, then I have to first calculate the derivative with respect to first, and then second by taking first as a constant, like that. Okay, so if parallelly if you check these two conditions, dou f by dou x equal to 0, dou f by dou y equal to 0, and if you this is nothing but this is the Jacobian matrix. Okay, and this, if this is positive, then only I can tell that as a minima. Now here you can see that you have to check the positive definiteness of this particular matrix, dou f by dou x square. So you have to know that how to calculate the positive definiteness of matrix about some point x0 and y0. And so for that purpose also the positive definite matrix is very, very important. Okay, so crux of the matter is that whenever you have to find the minima in higher dimensional space, at that time a natural condition that is coming from the calculus, you have some kind of matrix. Now you have to make sure that that matrix should be positive definite. And how to do that? You have to calculate the eigenvalue, you have to perform energy test, or you can go via pivot. Any way can tell you that whatever problem you have that has minima at certain point or not. Anyone has confusion on this? So in that way, positive definite matrix has several applications whenever we are going to talk about the minima. Okay, now last part of the today's lecture, I am going to show you that whatever energy function, what is shape of that particular energy function. What we have found, that energy function looks like this. Okay, but during the proof, Lyapunov proof, what we have found that suppose if I have region, then I have to construct whatever Lyapunov ball that is closed. Okay, so basically how these two things are related, we are going to show here. Okay, so if I have 2 cross 2 matrix, just we have seen that I have some kind of this kind of shape and equation is like this. Okay, now if I have constructed some kind of Lyapunov function using putting x and y, all possible value of x and y, then there some number comes into picture. Okay, for simplicity, suppose this number is 1, and after that I can obviously generalize. Okay, and here suppose matrix S, symmetric matrix associated with that I have represented like this, where eigenvalue is lambda equal to 9 and lambda equal to 1. Okay, so this is nothing but some kind of equation of ellipse, so that is called energy ellipse. And now if you see the graph of this particular function, where what we are telling that energy x transpose Sx is a ball opening upward, we have just seen it, cut through a ball of height this. Okay, so I have some kind of ball like this, and after that I am going to cutting this ball by this function x transpose x equal to 1, and after that it is possible to show that is converted like this. Okay, let us try to see this. So basically here directly I am coming here. So I have this kind of function 5x square 8xy 9y square equal to 1. Okay, so just I am going to see that here in unity, whatever energy ball I have constructed, I am assuming that their radius is unity. That I mean to say. So now if you see this, so I can able to represent this like 9x plus y square root of 2, 1x minus y square root of 2. Please just check it. Okay, because I have to I have to represent this in form of some kind of positive definite matrix. So a positive energy function, so greater than 0, and after that now you can see here that here x and y, so 1 by root 2, 1 by root 2, that is coming here. So this point, and after that this point, and 1 by 3 and 1 by 3 is axis of this. Okay, so basically what I am going to claim here, that if I have some kind of matrix like this, first you can calculate the eigenvector. So 9 and 1 is the eigenvector, and corresponding to that eigenvector, what you can do, you can eigenvalue, you can calculate the eigenvector. So I have two eigenvalue 9 and 1, and corresponding to that eigenvalue I have constructed some kind of eigenvector, that is 1 and 1 transpose and 1 and minus 1. Okay, and after that I am going to normalize it. And how to normalize it? You can divide by 1 by root 2 square of this. So normalization is 1 by root 2 and 1 by root 2. You can see that whenever I am converting into some kind of form like this, so here eigenvector is going to reflect, and here basically a scaling factor is nothing but, or here whatever scaling factor that is associated, that is coming from the eigenvector. So this is coming from eigenvalue, and 1 by square root, 1 by square root, and 1 by square root minus 1 by square root, that is coming from the eigenvalue. And I have cut that ellipse by energy of 1, and due to that reason I have this kind of ellipse, and you can see here the shape is like this. Okay, so what I mean to say here, I am going to put one remark, and remark is very, very important, and several times if you go somewhere, then people are asking this kind of question, that suppose if you have energy kind of function. Okay, so what is axis length? Okay, so axis length I can able to calculate from the eigenvalue, that is 1 by square root of lambda, and direction one can calculate from the eigenvector. Okay, so same kind of things we are telling here, that whenever you have some kind of positive definite function associated with some kind of symmetric matrix, so what we found, that length of this axis can be given by 1 by square root of 9. Okay, so somehow how much area that is covered by this kind of energy function, that is decided by the eigenvalue, and what kind of direction, because this ellipse is no longer this kind of ellipse, that is tilted ellipse. So how much tilting that comes into picture, that is due to vector. Okay, so using eigenvector and eigenvalue, and based on the energy function, I can able to also tell that what kind of shape comes into picture and what is the axis of that particular shape. Okay, so that is another important result. Okay, so whenever you are constructing some kind of energy function with help of some kind of symmetric matrix x transpose px, it means that what you are going to do, you are going to select your axis, even if any higher dimensional space. Whenever higher dimensional space we are telling that is ellipsoid. So what is axis of ellipsoid? That is decided by the eigenvalue. And what is direction? In which direction that will point out? That is decided by the eigenvector. And what we found, that if energy function has some kind of finite value, you can see that always I have some kind of closed structure. Okay, and now we are able to understand that whenever we are constructing some kind of energy function Vx that is less than equal to c, why that is, that I am going to represent like this. Okay, so that is another message from here. So please just now come to the last part of the today's lecture. This inequality is very, very important, and that is called Rayleigh inequality. So now what Rayleigh inequality is suggesting, that if you have some kind of symmetric matrix S, and if you construct some kind of energy function, I can able to tell that what is minimum and maximum bond of this particular quantity. This is a scalar quantity. Okay, so maximum smallest, that is bounded by what you can do, you can calculate the eigenvalue of this matrix S, and we know that that is always positive. So you put that eigenvalue here, minimum eigenvalue, and maximum here, and after that you can just multiply with the norm of this x. Most of time we are just talking the two norm here. Okay, so in this way I can able to tell that what is bond of this energy function. Okay, and proof is very, very simple. What we have seen, that whenever I have some kind of symmetric matrix, then I can represent that symmetric matrix using some kind of eigenvector, some kind of quantity matrix where each entry is diagonal, and this will represent some kind of eigenvalue. Okay, if you normalize it, then eigenvalue will going to multiply here. Okay, so and this is ortho. I have already told you that I can able to scale out eigenvector to unity, and because all are orthogonal, so orthonormal is also there. So Q is the matrix of eigenvector. This is diagonal matrix containing the eigenvalue. So I can able to represent like this. Now if I will write x transpose Sx, whatever energy function I have constructed here, so we are just going to see that why we are writing this kind of inequality. Okay, so now I know that if this is symmetric, so just we have seen that that can represented in terms of eigenvalue and eigenvector. So same kind of things I have done here, and after that what I am going to do, I am going to group Qx by Z. Okay, so if you will do that, then I have this kind of situation now. And what I know, that this diagonal matrix has just diagonal entry, and whenever and all diagonal entry, because all eigenvalue is positive. So positive means I have some kind of minimum number and maximum number. Suppose I have 2, 3, 4 like this, something like this. So I can tell that this 2, 3, 4 is not going to go beyond 4, 4, 4, and all other entry are 0. So less greater than this, and after that 2, 2, 2 like this. And if you take common, then what happens, 4 into identity, and here 2 into identity. So same kind of things I have written. If you have lambda, then take the maximum value of S and multiply with identity, so that is upper bound, and multiply with the lower value, then that is lower bound. And after that what you can do, now both sides you can multiply with Z transpose. So Z transpose here, if I multiply, then Z transpose comes into this Z. If I will multiply, then this kind of things comes into picture, and this is a scalar quantity, so take it out. So Z square, now I have Z transpose Z, and we know I have already defined Z equal to Q into X, and Q into Q transpose equal to identity. Due to that reason I have this kind of things. Okay, so due to that reason I have this inequality, that is called Rayleigh inequality. And believe on me, in this whole Lyapunov analysis, several times I am going to use this kind of inequality. Okay, so several times I will repeat. So this is just proof of this. So please again go through this proof. And after that, if you have some kind of time varying matrix empty, so that is positive definite. If I uniformly positive, uniformly means for all t, positive definite if that will satisfy this kind of condition. Okay, so now I am going to conclude the today's lecture. So what basically we found in the today's lecture, that how to define positive definite matrix. Okay, so positive definite matrix is nothing but where all eigenvalue that is positive. Okay, after that what we found, that how positive definite matrix is connected with the energy function. So energy test using that, and after that just by seeing the leading diagonal, okay, how one can talk about the positive definite matrix, and how minimum problem is related to the positive definite matrix. Okay, and based on this I can also able to construct the Lyapunov function, and with the help of the Rayleigh inequality. Okay, so in next class I am going to talk about that definite construction of, means I can give guarantee that if I have some kind of linear system and if that is stable, then what is form of the Lyapunov function. Okay, that kind of things I am going to discuss in the next class. So with this remark I am going to end the today's lecture. Thank you very much. If you have any question, then please let me know. Okay, if you don't have question, then please go through lecture and after that you can ask. Okay, and this is very important topic of linear algebra. So you can read this topic from any standard book. Okay, Gilbert Strang is very nice for this particular positive definite matrices. Okay, so please go through that. So thank you very much.